Welcome to Jones Math Ed Problem Solving. Today we are going to be talking about Babylonian fractions and repeating sexagesimals with Dr. Jones and Lucy. So anyway, as we know, sexagesimals notation. Sexagesimal means basically base 60, like base 10, but with base 60. I'm going to stop writing in that because that marker isn't very good.
Okay, I'll throw it
So
away.
anyway, sexages means 60, and imal means like part of, and something like that. Sort of how decimal means 10 and part of. So it is like base 10. So when the Babylonians wrote, they had their 3600s, they had their 60s, and they had their ones.
And it could keep getting bigger.
And ... basically.
So how did they do things that were smaller than 1?
Well, they put this semicolon here.
Technically, I put the semicolon there.
Well,
the Babylonians didn't, but yes.
That's in essentiality what that means. It's like a decimal point.
Okay. So since we're not in base 10, we're going to use a different symbol.
160s.
Okay.
You have your 1/3600s.
Hang on. You wrote 3600s, not 1 over 3600s. Okay.
There. And then that continues on as well, but I'm out of room.
Okay.
So basically, if you were to write 1/10,
okay, that's a fraction in modern notation. How could you write that in sexagesimal?
Well, basically, you want to get over 60.
Okay.
Now, how we get from 10 to 60 is times 6.
Okay.
So 1 would be times 6, and that would be 6/60ths, or 0 and 6/60ths.
Okay, great. Could you do, how would you do 1/5?
1/5.
Yeah.
Of course. Okay. Let's see. Equals 60. So anyway, how we get from 5 to 60 is times 12. So 1 times 12 is 12. So that would be 12/60ths, or 0 and 12.
Great. One more. What about 1300s?
1300ths. Yay. So
Could we put it into 60ths?
no.
Why not?
Well, because
Like if I wrote equals...
we need to have a whole number, and if you multiply this by what is it?
6/10?
6/10.
Then you would get, that's not a whole number.
Yes.
Okay. And we want to get a whole
see.
number.
13 times.
It's not on.
Oh, that's embarrassing. So 13 times 6/10 is 7.8, which is not a whole number.
It would be, it's true that it's the same as 7.8 over 60, but it's not what we want. Okay, so instead of using 60 there, what can you use? 3600, okay.
3600. So that would be times 36 times 36. Now 13 times 36 is 468.
Great.
But we've run into another problem.
So right now this would look like 0 semicolon 0 because there's no 60ths, but 468 in the 3600ths. You say there's a problem. What's the problem?
Well, if you can't have more than 59 in here, so it would have to be...
Because it's a base 60, right?
Less than 60 in this place.
Okay.
So we could have 59 or 0 to 59.
Okay.
And that's it we could have in this place. So we need to divide this by 60. Well, that's a square root sign. But 60.
Yikes. Okay.
Yeah. Okay.
Get that calculator out. Get it on the screen for us there.
Okay,
All right.
so 468 divided by 60. And what that gives us is 7.8.
Interesting. Okay. So what do we do with that 7.8?
We put the 7 here and we put the 8 here. Yay. Okay.
Maybe. So the 7, yes, because there's 7 groups, 7 whole groups of 60. So 0, 7, and then hang on. Okay, so we took 468 and divided it by 60, and we got 7, and then how much is left over? 7 times 60 is how much?
420.
Okay.
So we have 48.
Where's that 48 coming from?
Well, 468 minus 420 is 48.
Oh, I see. So put a 48 right there. Great.
Yay.
Okay. Let me show you another way to do this. If we are, we're going to use our calculator here, we could take 1300ths, and you get a decimal right there.
Mm-hmm.
If we were doing this with base 10, and we were asking, well, how many tenths are there in 1300ths? We could multiply it by the base, and we get 1.3, so 1 in the tenths place. Subtract out the 1, multiply it by 10 again, so this would be in the hundredths place. We get a 3. It's like, whoopee! 1300ths is a 1 in the tenths place, and a 3 in the hundredths place. That's not a big deal because we all work in base 10 all the time. Okay, whoops. But let's do it this way, 1300ths. And if I multiply by the base of 60, keep getting that number. So we'll take the 7 and we put it in the 60th place.
So
Subtract
is
off the
this
7.
equivalent to 1300ths? Or
let's see. I've got the 8 here. I want to answer your question, but I'm in the middle of doing something else. Can I do the other thing and then come back to your question?
Sure.
Okay. I wrote a 7 in the 60th place, and then I subtracted off the 7, and now I multiply by the base again, and I get 48. There we go. Okay, you asked a really good question. Is this the same as 1300ths? So that means 7/60ths. Okay, so that means 7/60ths. That's what the 7 means there.
Yes. 7/60ths.
Can you write that as a fraction? 7 over 60 plus 48 over 3600. What's a good common denominator between those two?
3600.
Okay. So that one's already
we
in
multiply this by 6.
60.
D.
Uh-huh. Yeah. And multiply the denominator by 60.
So 7 times 60 is 420
Uh-huh.
plus 48, which is 468.
Okay. 468 is the numerator. What's the denominator?
3600. So they are equal.
They are equal.
So let's just turn that into an exclamation point.
Okay,
So
but it's not
a question.
factorial, right? Okay, cool. So now, let's try that. Let's try doing that. Let's take, here's a sexagesimal number, 6 semicolon 3 comma 15. Can you write that as a decimal?
Possibly. Okay. So, so this is obviously going to stay the same.
That's the whole number. Okay.
Because the whole numbers don't really change if they're under 60 over here. So, this, as we know, is over 60, and this, as we know, is over 3,600.
Okay.
Which is a lot. Anyway. So, to get from here to there, that is, times 60 times 60. So, let's bring this over. 3
Can you
times
move it over so we can still see what you have? Okay.
60 is 180. So 180 plus this 15 that was already there. 195.
Okay.
Now, to get it from here to there in decimal form.
Okay, so first let's write it as a, let me say, as a decimal, and I'm also interested, can we write it as a modern fraction? So, where's this 195 live in the fraction?
It lives right there.
Numerator, denominator?
It's in the numerator, so
okay.
we need to put it over its denominator, which is that.
Okay. So can you write it as 6 and, can you write it as a mixed number? 6 as the whole number, and then the fraction you were talking about? Well, we don't have to put a decimal point.
I know, I just realized that. So anyway, 95 over 36.
Okay.
Okay.
Cool.
So do you want it as a mixed number or
so
an
that's
improper fraction?
that's the mixed number right there.
But
I'm okay
anyway.
if I don't really want it as an improper fraction.
So anyway, 195 divided by 3,600.
Okay.
That is not a pretty decimal.
Okay, that's not. And it's probably not even a terminating decimal. My guess is that 6 actually repeats, and the calculator's just rounding that. So this would be some sort of repeating decimal right there.
So this would be the type of thing.
Well, the Babylonians have a sexagesimal that does stop, but it turned into a decimal. Let's see, 6.05416, and we put a little bar over that.
Yes.
To show that's repeating.
So that is our decimal.
Yep. That's our decimal version.
But
so now, oh, go ahead.
What if we had, you said something about how they wouldn't do sevens.
Oh, yeah. So Babylonians actually didn't deal with repeating stuff very well. So they liked 1/2 because that's the same as 30/60ths, or they would write it with their symbols, of course, but in sexagesimal notation for us, we use the Hindu Arabic numerals, 30/60ths. Or 1/3, they like that.
Because it's 20/60.
20/60ths. And 1/4, they were cool with that. 1/5, 1/6.
Yes.
But 1/7, 7 doesn't go into 60 evenly. And it doesn't go into 3,600 evenly. In fact, because 7's a prime number that's not a prime factor of 60, then it doesn't work out.
So
we can do...
They just didn't use 7.
They just didn't use 7s or 11s or 13. They said if you want to divide by 7, then don't divide by 7. Divide by 6, divide by 8, maybe pick a number in between. So they just ignored those.
So did they not divide by prime numbers that did not go evenly into 60?
That's correct. And some people think, but nobody really knows, that the reason they used sexagesimal notation was because they can evenly divide 60 by lots of numbers. 2, 3, 4, 5, 6, 10, 12, 15, 20, 30. And so some people think that's why they did that. Now, if we wanted to get if you had to get a sexagesimal for 1/7, we could do long division.
We could.
We could. So 1 divided by 7 is, you can't do it. So there's no 7s in 1. But I'm doing sexagesimal, so I'm going to put a semicolon and put a 0 here.
But
this looks
turns
like
into it. This looks like a 10, but it turns into it multiplies by 60, so it would be 60 right there.
So this is 60 60ths right there. Yep.
Yes.
So I'm regrouping the 1 into 60. So then I think, how many 7s go into 60?
8.
8. And 8 times 7 is 56. Whoops. And so 60 minus 56 is 4.
4. So we add another 0, and we multiply it by 4. That gives us...
Yeah, we regroup the 4 over here. 4 times 60.
240.
240. We think, how many 7s go into 240?
34.
How do you know that? Because we did it already.
Yes, but...
240 divided by 7 is 34.
So 34 times 7 is 238.
We're left with 2. And we regroup the 2 to be how many of these?
120.
Yeah, we just keep multiplying by 60.
So that one, 7 goes into 120 17 times.
17 times.
Now 17 times 7, that gives us 119. So we have 1 left, and now we're back to where we started. So this is a repeating.
It is repeating. You said we were back to where we started because if I put a comma 0 there, or maybe even I don't put a comma 0, we started with 1. So we know this pattern is going to go 8, 34, 17.
So this is our repeating sexagesimal.
Yeah, so now we're doing stuff with Babylonian numerals that the Babylonians didn't even do. We could write it with our notation with the bar over it, or we could also write 8, comma 34, comma 17, comma 8, comma 34, comma 17, dot, 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 something like that. Okay, let me show you something cool on the calculator.
Mm-hmm.
So this number was 1/7.
Mm-hmm.
And if I multiply it by the base of 60 that I'm looking at, that gives me 8. If I subtract off that 8, I get this long decimal. Multiply it by the base again, I get
Weird.
34.
That's wacky.
That is wacky. Thanks for using that modern day kid slang. Subtract off 34. If I want to know what's in the next place, I multiply by the base again.
17.
I'm going to subtract off 17.
And then you multiply it by the base again, and it just keeps on going.
Yeah. Actually, it should, theoretically, but the calculator is going to break down in a little bit because it doesn't store long, like many digits of numbers, because we are now in this is 60 to the 4th power. This is some like 1,296,000 or something like that. Yeah. So
wow.
12,900,000, we're very small. So if I go back to, how do I go? Hang on. Yeah, okay. So if I were to ask for 1/7 times 60 minus 8 times 60 minus 17 times 60, nope, I just 17 and 34. Wasn't looking. 1/7 times 60 minus 8 times 60 minus 34 times 60 minus 17 times 60. So far it's okay, it's 8. Minus 8 times 60. I got 34 again. Minus 34 times 60. I got 17 again. Minus 17
times 60.
Times 60. I got 8. Minus 8. Maybe I lied to you. Times 60. Oh, 33.
That's wacky.
That is wacky. But we went a long time, so the calculator doesn't have an infinite capacity. We know from what we did with long division that this actually will repeat. Okay, let me show you one more thing. If you like wacky, you're going to like this.
Okay. Now.
So just to remind everybody what we've done, we took one of our modern fractions and put it in sexagesimal. And we also took a sexagesimal and wrote it in our modern terms as a fraction and as a decimal. Now we took a modern fraction that became a repeating sexagesimal that the Babylonians actually would never deal with. So now I want to look at if we wanted to write a repeating sexagesimal as one of our modern fractions. So I'm going to look at this one.
Difficult.
Okay, so I'm taking this number right here.
So every time it gets...
That's 5/60.
60 times smaller?
That's right, 60 times smaller. I'm going to use exponents.
Yes, exponents. Exponents are groovy.
Okay, so that's what this number is. If I call this number x, kind of like I'm doing an algebra equation, I'm saying x is equal to that number. Okay?
Yes, okay.
All right. Now what I'm going to do is something really weird. I'm not going to try to get a common denominator for these because I actually have an infinite string of them. And so
yes.
I could never do that. So instead what I'm going to do is I'm going to multiply both sides by 60.
Both sides by 60.
And here's what that's going to do.
Like we did with the Egyptian numerals?
Kind of like we did with the Egyptian with the key fact, yeah. So if I multiply 60 times x, I just get 60x. If I multiply 5/60ths times 60, what do I get there?
60ths times 60.
5/60ths times 60, what do I get?
Well, that would be 5 times 60.
Hang on. What happens to the denominator and the numerator here? So you took 5 times 60.
That's 300.
360ths.
Yes, 360ths. So,
360ths is 5.
Yes, 360ths is 5. Yes, good.
Okay. And does that make sense? 5/60ths times 60?
Divided by 5 would be 5, yeah.
And I could even cancel those 60ths.
Yeah, so that would be 5 times 1?
5, yeah, 5 times 1.
Yeah, 5 times 1. No,
Okay.
5. Wow.
If I take 5 over 60 to the second power times 60, that's going to give me 5 in the numerator and only 60 in the denominator because one of the 60s will cancel with that 60.
Oh.
And then I get 5 over 60...
To the third power.
Well, it was to the third power.
No, but we canceled it out.
Uh-huh.
So now... Oh!
Well, not fourth power, third power.
So you're taking this 5 and you're passing the denominators down.
That's right, by multiplying by that base right there that we had.
That's wacky.
It's wacky. You know what else is wacky? That whole thing that goes on for an infinitely long amount of time we've seen before. That is this number right here. Do you see that? Not the 5 part, but the 5/60ths. That. Where's the 5 over 60 to the fourth power?
It would be right
Yeah, it'd be in the next spot. So I could rewrite this equation as 60x equals 5 plus x.
Wacky.
Is that something you know how to solve?
Yes, actually.
Okay.
So we have 60x equals 5 plus x.
Okay.
So we try to get this x over to there.
Okay.
So so we add negative x.
Okay.
Negative x plus 60x. So would that be 59x? Okay, 59x equals 5.
Okay.
So now we divide both sides by 59. We'll be left with x equals whatever number that is.
No, well, I wanted it as a fraction.
Well,
So that's a fraction, right?
5/59.
Yep. That's the fraction that we get, not the decimal. I'm not really interested in the decimal because it's nasty.
An ugly decimal.
It's a very ugly decimal. But that's 5/59, and that's equal to x, and x was also this number. So that means that maybe 5/59 is equal to, maybe, 0 semicolon 5 repeating.
Well, based off of what we did, it makes sense.
I'm really glad that you put 5/59 into the calculator because I want to check this using that multiply by 60. I get a 5 in the 60th place.
Minus 5.
Subtract the whole number.
Times 60.
Yep.
Wow, that's wacky.
Do you want to see something that's groovy? Look at the decimal that we got. When we took 5 divided by 59, you got 0.084 blah, blah, blah. It's 0.084 blah, blah, blah. If I subtract 5, I get 0.08. I keep getting the same number. Now, eventually, the calculator will stop doing that because, like I said earlier. Okay? You want to try one more?
Sure.
Okay.
Will this one be even wackier?
It will be weirder.
I need to come up with a different catchphrase now.
0, 5, 10, 5, 10. So where the numbers repeat, but not every place value, but it skips one. Okay?
So
I'm going to say x is that
instead
number.
it would be, say if they did the repeating bar.
It would look like 5, 10 with the repeating bar there.
Yeah.
Okay.
So, that's a little spooky.
Okay. So if I compare it to this problem, when I multiplied by 60, it shifted everything over one spot. So now I don't really want to shift everything over one spot.
You want to shift it over 2 spots.
Yeah. So what do you think we should multiply by?
I think we double the exponents.
What do you mean?
Well, I don't know. Let's say these are all.
So that one, are you talking about that as a fraction? 5/60 is 60 to the third power?
Yes. And then this one would be. So all of these would be odd exponents. And all of these would be even exponents.
Okay. So what would I multiply this denominator by to get to that one? To get from 60 to 60 to the third power.
You'd put it to the third power to get 60 to the third power?
Yeah, but this is like 60 to the first power.
So, let's see.
What does 60 to the third power mean?
Well, the way I learned it, exponents, like,
say 60 to the third power.
60 to the third power.
What does that mean?
60, that's a 60 times 60 times 60.
Cool. Yeah, that's how I learned it too. So what would I need to multiply by 60 to get 60 to the third power?
This part right.
Yeah, you already have 160, so, and we could write that as, with exponents, as 60 to the second power. So.
Oh, so you multiply this by this to get to.
You do, but that's kind of it kind of just happened that way.
Well,
I multiply, what happens if we take 60 squared and multiply it by 60 squared? 60
squared.
Do we get 60 to the fourth power?
I don't know.
Look at your exponents. Think about the exponents. 60 squared, 60 to the second power, times another 60 to the second power.
Well, this would be 2 60s, 2 60s. That would be, all in all, 4 60s.
So does it work?
Yes.
Great. So multiplying by 60 squared is going to help us out here. So our number that we were looking at before was 5/60 plus 10 over 60 squared plus 5 over 60 to the third power plus 10 over 60 to the fourth power, and keeps going. And if I multiply both sides of this by 60 to the second power, and there's an infinite number of things inside that parentheses.
That's a very large parentheses then.
This is 3,600x. I'm just taking 60 times 60. If I take, and so I could think of that as 3,600. If I take 3,600, well, actually I want it as 60 squared, times 5/60, what does that give me? What does that say? I can't read it.
Did you mean for that to be separate from that?
That's how I wanted to write it.
Okay. That would be 300.
300.
But that would be 3,600 times 5 divided by 60.
So that's 3,600 times the 5 divided by the 60. That's what I wanted to do.
Oh, okay.
Now, a shortcut would be I could cancel one of the 60s here, and I'd be left with 60 times 5, which is still 300. 10 over 60 squared times 60 squared, the 60 squared would cancel. And I would just be left with 10.
Weird.
5 over 60 to the third power times 60 squared, 2 of the 60s would cancel. I'd be left with 5 over 60.
So it's like with the other one. So this one changes. The first one changes to a whole number. Then the second one also changed to a whole number. But the rest of them just like pass down there.
That's right. That's why I picked that number 60 squared.
It's like the one we just did here.
Yep.
Strange.
3,600x is 300 plus 10 plus all of that is just x.
So
can you solve that?
Yes, I can. I'm going to solve it in purple because that's the marker that I had. Okay, so these two we can combine to be 310 now plus negative x plus.
Okay.
So this one would be
so 3,599x equals the 310. Is that what you're saying?
over 305. Okay, yeah.
So you're dividing that. What are you doing on this side?
Doing the same thing.
Okay.
Now, anyway, here's your fraction.
Okay, so x is equal to, write that fraction for me. Okay, I don't want it as a decimal. I know, because I've done this problem, that this is going to be a nasty repeating decimal. But I would like to check and see if it checks out.
So, 310 divided by 3,599 times 60.
Yeah. Oh, good.
Minus the whole number.
Which was a 5, which is what I wanted to see. I'm really hoping you get 10.
60. Yay!
Yeah, and then that, when we subtract off 10, don't do it yet, we subtract off 10, we get 0.086, which was the number we had up before. So it did work.
Groovy.
Great. Thanks so much for helping me with that.
You're welcome.